Okay, so this is some exam feedback for the 2006 Chemical Oceanography exam. So this is mostly for next year's students to use for revision, but hopefully this will give you some ideas of the kind of things that I was looking for with the exam questions. Okay, going on to the here we go. Yeah. So first of all, there were these two short questions, and then you had the option of two longer questions. So the first two questions were these. One was about the properties of water, why it dissolves salts, and diffusivity, and the other one was about residence times. Okay. So if we just go through those in turn and think about the individual questions. So one of the things you really should do with exam questions is really read the question and try and pick apart what it's actually asking you to do. Okay. So if I just go and get a pointer here, give myself a pointer. Okay, so this question here has got two parts. So the first one is we're asking you to explain. That's a key word there. Okay, why water is good at dissolving things. Okay, so one thing is why it's good at dissolving things, and then the second part of the question is about diffusivity. And why is the diffusivity of salt low? Okay, so we're really asking you why salt diffuses slowly compared to heat diffusing through water. And there was a little bit of confusion about what was actually meant by that in some of your answers. So going on to answer the first part of that question, why is it good dissolving? So things that you should be thinking about here is the water. Just go back to giving myself a pointer. So water here, the water molecule is slightly polar. Okay, so it's got positive charges around the hydrogens because the electrons are shared here with the oxygen, and then you have these paired electrons over the other side, giving this side of the molecule a negative charge. And this is what results in kind of water molecules kind of clumping together, which we'll come to in a bit, because they kind of got opposite charges. But specifically for this question, we're asking you why it's good at dissolving common salts. So the first thing is that these polar water molecules can basically pluck out the individual atoms from the salts to get them into the solution. Okay, so because you've got the positive sides of the water here attracting, in this case, a chlorine ion, and that can pull it out from the crystal lattice. So that's why it's good at taking things out of the solid phase, but also water is really good at keeping things dissolved. So this is why it's such a good solvent, is that once an ion of chlorine or sodium is taken out of the crystal lattice and it's dissolved, it's surrounded by water molecules. Okay, so that surrounding by water molecules should form part of your answer as well. That's kind of a diagram of that here, taken from the lectures. Okay, and this isolates the chlorine and the sodium ions, so they can't recombine and precipitate out again. Okay, so that's what makes things soluble. So those are the things that are required for that part of that question. Okay. Now the second part of the question was the bit that was answered the worst, really. So quite a few people went off and described a whole bunch of things they know about water. So it's high heat capacity, it's got a high boiling point and melting point relative to other similar molecular weight substances. That's maybe correct, but it's not specifically answering the question. Okay, and that's really what we want you to be doing. We want you to specifically answer the question we ask, because if you don't do that, you don't get many marks or any marks. Okay, so what we're really asking here is about the diffusivity of water. Okay, diffusivity of salt in water and relative diffusivity of heat in water. Okay, so that's what ended up we demonstrated this in the class by showing these this salt fingering. Okay, where you get the diffusivities of the two different things are different. That causes one to sink and one to rise up again. So I'll put a link of the video of that in the description, and also probably should be linked if you click on that image there. But what we're really getting at here is one of the properties of water is that you get these large clumps of water that are bonded together by hydrogen bonding. Okay, so these are the polar ends of negative ends and positive ends of the water molecules basically attract each other together, and that forms these large clusters of water, which is not quite kind of like solid lumps, but they're kind of water is not individual molecules that kind of float around freely. Okay, so heat can diffuse through, can get from one side of a cluster to another side of a cluster relatively easy, because heat is just transferred from one molecule to the next by shaking. Shaky. Okay, but to get salt from one side to the other, you've got to actually physically get the sodium ion or the chlorine ion through this cluster of water molecules, and that's quite hard to do, especially because those ions are actually surrounded by their own kind of larger clumps of water. So it's this clumpiness of water that is the key thing that you needed to have in your answer here. Okay. Okay, so the second question was really about residence times. Okay, so once again, a couple of parts to this question. So I'll go back to my pointer here. Get myself a pen. So okay, so really we want you to define. Okay, and there are two things that you need to define here. We need to define what we mean by residence time, so that's one thing, and we want you to define what we mean by mixing time. Okay, so those are two things that need defining. Okay, and then the second part of the question is asking you what assumptions, okay, when calculating residence times. Okay, so those are the things that we need in our answer. And these are the kind of the slides from the kind of lectures which are kind of relevant to this. Okay, so residence time is defined by this equation down here. So that would be a really good thing to have in your answer. Now, quite a lot of mistakes were made with this term on the top here. Okay, so what this is the amount of the element that you're interested in the reservoir. It's not the total size of the reservoir. It's not the volume of the ocean. Okay, it's the amount of that element that is dissolved in the ocean. It's not the concentration. Okay, it's the amount. So another way of describing the residence time is the average amount of time that a particle of that element or a particle of that substance is in that reservoir before it is removed by the flux out. Okay. So you needed to have that kind of description, and having the equation would have been nice as well. And then the other part, which was the mixing. Okay, so quite a few of you kind of didn't have great descriptions of what mixing time is. So really, it's kind of described by this slide here from the lecture where we had. I'll give myself the pointer back again. Where we had, how long does it take for the two different components of your coffee to mix together and become homogenized. So quite a lot of you, had this kind of description here where you said mixing time is the time for a substance to be mixed, which is kind of true, but what you're using here is you're using a definition that has what you're trying to define, mixing time, and the word mix as the answer. So it's like saying the colour blue is blue because it's blue. Whereas it would be much better to describe, in terms of the mixing time here, describe what it is without using what we call it. Okay. Okay. So moving on now to the longer questions. So these required a little bit more time. So you should be spending twice as long on these questions as you were on each of the other ones. So it's kind of the first two questions are worth the same amount as one of these last questions. So you should have planned that in your exam technique, kind of like when you're reading the exam at the beginning and deciding which ones you're going to do. Right, so we'll just go through these in turn. Okay, so the first question is about carbon dioxide in the atmosphere and how that is controlled by stuff that goes on in the ocean. Okay. So what I'm going to do is just going to pick apart this question and kind of rephrase it in a different way. So the things we're looking for are environmental conditions changing. So those, we need to have some of those in our answer. We need to think about processes that happen within the ocean. Okay, so we're going to think about how we might describe those. and what those might be, but we have to refer to these things when we're basically, these things at the bottom are the things that the question is actually asking. Okay, so changes in the Earth's atmospheric, changes in the CO2 content of the Earth's atmosphere. Okay, how is that changed by things that happen in the ocean? Okay, and we're going to consider environmental conditions and ocean processes. Okay, and then the second part of the question is really, how does the dissolved inorganic carbon change within the ocean? Okay, so these are the questions, but we have to answer them using these kind of pointers. Okay, so really what we're looking at here is things like the carbon pumps. Okay, so these are the organic carbon pump and the inorganic carbon pump, and these are things that affect the concentration of CO2 in the surface ocean. Now, quite a lot of you answering this question, you kind of missed out on the concept. You kind of didn't really distinguish the shallow ocean from the deep ocean. Okay, so some of you had some great descriptions of parts of the carbon pumps, or the organic carbon pump and the inorganic carbon pump, but you didn't really explicitly say that what matters is only the surface ocean can exchange with the atmosphere. Okay, and if you can put carbon into a form in the deep ocean where it can't interact with the atmosphere, then that isolates it from the atmosphere. That will reduce the atmospheric concentration. Okay. Another bit that most people got, but a few people missed out on, is that actually this diffusion in and out of the water, that is also an important control. Okay, so this is Henry's law, so that the concentration in the atmosphere is equivalent to the partial pressure in the dissolved in the ocean times some solubility constant, and that solubility constant is dependent on a bunch of environmental parameters, temperature, salinity, those kind of things, which would have formed part of your answer. Okay. Also, kind of the efficiency of this exchange here is dependent on things like the physical conditions at the ocean surface. Okay, but the bulk of your answer should have really focused on about how we can change the concentration of CO2 aqueous in this surface layer, because only that can exchange with the atmosphere. So this is basically taking carbon and exporting it down into the deep ocean, either through the organic carbon pump, okay, which is described here and also in the lectures, but also by the inorganic carbon pump. So this is changing the relative species of the dissolved inorganic carbon. Okay, if you put most of the carbon away in species like bicarbonate and carbonate, which can't interact with the atmosphere because they're not CO2 and they're not gaseous, then that can affect how much is in the atmosphere. Okay, and all of the things that then control that speciation. So these are things like this. So the pH of the ocean determines how much of the total inorganic carbon in the ocean is CO2, and how much of it is these other guys. So if you have more acidic ocean, you have more aqueous CO2, so more can interact with the atmospheric CO2 goes up. Okay, and quite a lot of people kind of got a bit of a mention of that, but didn't really fully explain and describe how these reactions over on this side, particularly these dissolution and precipitation of calcium carbonate. So this is the inorganic carbon pump. This is the formation of shells, of tests of foraminifera, of corals, how that affects the speciation here, and ultimately how much CO2 goes into the atmosphere. So that needed to be explained. It would be really good for having your answer all of these equations. Okay, so that would have been really, if you could not just write the equations down, but write the equations down and then describe their effects on atmospheric CO2. Yeah, so once again, just to go back and mention this exchange with the atmosphere. Okay, so that's dependent on temperature via the solubility pump. Quite a lot of you kind of missed that out. An easy few marks there. And the last part of the question is how these environmental conditions, so things that affect, so quite a lot of you mentioned the organic carbon pump, but what are the controls that determine its efficiency? Okay, so one of the key things is this inorganic to organic carbon ratio, the amount of primary productivity. These things are important for getting like the full set of marks. Okay, so last question, question 4. So once again, I'm just going to just going to break apart this question. So using summary chemical equations and diagrams, so that tells you that your answer must have equations and diagrams. How nutrient concentrations are related to oxygen concentrations in the ocean, okay? And where does that relationship break down? So to just kind of jig that equation. So the main part of it is how and why are nutrient concentrations related to oxygen. So nutrients, oxygen, how are they related to the ocean, and when are they not related to each other at all? Okay, and then as part of your answer, you have to use chemical equations and you have to use diagrams. Okay, these are how the marks are picked up. So really, this is the key kind of overall kind of summary equation that explains this thing. So when biological activity happens, so this is photosynthesis. We have this process that takes nutrients, okay, and it forms organic matter with those nutrients, okay, and it takes up CO2, but it's most important for this question, we're taking up nutrients and we're producing oxygen. Okay, so this equation predicts when we have photosynthesis happening, the concentration of nutrients should go down and the concentration of oxygen should go up, and conversely when we have respiration happening, we would expect oxygen to be used up, oxygen concentration would go down, and the nutrient concentration of the water would go up. Okay, so this is kind of what we see in parts of the water column. So another kind of good diagram to have in your answer would be something like this. And quite a lot of you did this. Obviously, you'd want to have lots of annotations that describe all of these things, and I won't go into what those are now, but you should be able to get those from your lectures and whatnot. But really, we're looking at places where these curves are related to each other, or have this inverse relation. So when one goes up, the other one goes down. Okay, so we can see that in this deeper section here, where just below, this is the pycnocline or thermocline, we've got the mixed layer of water above, so light comes in the top, and kind of water is well mixed in this layer here. Lots of biological activity is happening, and so we can see here that at the base of the pycnocline we have this peak in oxygen, and that's because that's where most of the photosynthesis is happening. Okay, because there are available nutrients there. The nutrients are lower in this zone here, they're declining, and that's because they're being used up by all this photosynthesis that's happening. Okay. If you go down into the ocean, we've got a reduced oxygen concentration. That's because all of this organic matter is being kind of used up by respiration, and that's releasing nutrients back into the water. So in the lower part of this graph, you can see that this form is the opposite kind of form of this form. And that's because in this part of the ocean, this is where this respiration process is dominating. Okay, so this is where there is this relationship between nutrients and oxygen. Okay, so that would form kind of the basis of the bulk of your answer. We have those annotations again. So now we need to think about where this relationship breaks down. Okay, and the first thing to notice is that, you know, actually at the very surface of the ocean, we don't have this kind of nice inverse relationship between nutrients and oxygen anymore. And that's because there's a process that's happening that is not just this equation here. Okay, so this is the equation for a summary for respiration. So we take an organic matter that's got some nutrients in it, we use oxygen to respire that, and we release those nutrients back into the water. So that, if we have a process that's adding oxygen or taking away oxygen that doesn't involve this nutrient-rich organic matter, then the relationship will break down. And at the surface of the ocean, that's exactly what happens, because we have gaseous exchange with the atmosphere that adds oxygen to the ocean, but it's not taking away nutrients. Okay, so that's the first place where it kind of breaks down, and that's really one of the places where quite a lot of people missed out on some really obvious marks there, because there's this basically any addition or subtraction of nutrients or oxygen that is not due to photosynthesis or respiration, okay, is where we're looking for. So similarly, quite a lot of people mentioned trophication and having this when you get a lack of oxygen. Okay, now this was mentioned by quite a lot of people, not really fully described in enough detail. Okay, so what happens in these environments? We have lots and lots of nutrients that go into the ocean, and in fact, that is a place where this kind of equation kind of breaks down. Okay, if we're going to somewhere in the ocean where we're, like, for instance, in a coastal zone, estuary or something, and we're just adding loads and loads of nutrients because it's where the nutrients are being added, that those nutrients are not being added by this breakdown of organic matter. So in those environments we might have a breakdown of this relationship. Then further on from that we might have a situation where there's lots of biological productivity, and that creates lots of organic matter that sinks down into the deeper parts of the ocean, or the bottom in estuaries, and we use up all of the oxygen by respiration. Okay, so that means that once the oxygen gets to effectively zero, then we might still have some organic matter that's left, okay, and that will want to be respired by other bacteria that don't use oxygen. So we can't lower the oxygen concentration anymore because it's already zero, but the nutrient concentration can still kind of go up. Okay, so because we carry on respiring all of the organic matter due to these alternative, basically, oxidizers that are not oxygen. So denitrification, manganese ion reduction, those can remove the organic matter, release nutrients into the water without taking out any more oxygen, because there's no more oxygen to take out. So that would be one way that the relationship breaks down here. Another way is that there's another process that goes on in these environments that affects the concentrations of particularly nitrate without affecting the concentration of oxygen, and that's denitrification. Okay, so actually if there is any nitrate remaining in the water column and you've run out of oxygen and you still have some organic matter to respire, you can basically breathe that nitrate. Not you, but the bacteria that do that. So in this case that might cause the oxygen concentration to stay the same at zero, but the nitrate concentration might be changing in that water mass, okay, as it's being used by denitrifiers. Okay, so that would have been another place where this kind of thing breaks down. Okay, so that would have formed quite a good answer. Quite a lot of people mentioned upwelling as one of the reasons where this kind of breaks down, and that might be true, but it's not necessarily true. So imagine if you just take some of this water from the bottom down here and you bring that up to the surface. Okay, the concentrations of oxygen and nutrients in that water will still be related to each other by this the process of respiration and photosynthesis. Okay, because they are set by that process before they've upwelled. Once they have upwelled, then it might be that stuff can happen that stops this relationship holding. So it could be that you have input of oxygen from the atmosphere, or you have so many nutrients that the surface becomes suffers eutrophication, and you get anoxia near the surface, and then you have all those processes going on before. But that wasn't really explained very well by people in their exam answers. Okay, so just by saying there's some upwelling and that causes there to be this breakdown of the relationship, you have to explain why the upwelling will cause that breakdown. Okay, so that's the end of that. So hopefully this has been useful. You'll be able to take some of the kind of the outline answers that I've given here and compare that to what you wrote in your answers for the exam, and yeah, so hopefully the feedback has been useful. If not, then there we go. Yeah, I'm always available for you guys to knock on my door and whatnot. Anyway, end of that. How do we stop there?